please continue.
So, yeah, we keep getting like an inch or two of snow, and then it all melts, and the entire yard becomes a mud pit.
Yeah, and the dog runs
And
out
then
into the mud pit.
there, yeah, yeah. And our backyard, I'm pretty sure I'm gonna have to regrass seed it
Yeah,
because
yeah, I'm gonna have to do
it's
that
just
too.
gruesome.
And then try to
The
keep the dogs out of the new grassed area is
Yeah,
madness.
yeah. I like wish that I could just hit a reset button on my backyard
You
and
can,
start from
you
scratch.
can, you can.
I
You can hire
can.
some group to come in, and they'll bring a bobcat. They'll scour your backyard to dirt. They'll dump a bunch of topsoil on. They'll hydro seed this stuff that's like grass seed mixed with fertilizer that sticks to the ground, and within about 3 weeks, a month, you'll have a brand new lawn that is in perfect shape.
So the problem with that idea is
The
all of
vast
the
expense.
flagstone and brick in our backyard
Yeah,
that
that'll all
like
just get
we've had
torn up.
people come in. Oh, they're like, okay, so you're gonna have to remove all of this first, and it like quadruples the price.
Right.
So for the simple reason that we have like 100 years of brick stuff put into our backyard.
Yep.
So this is more of a every weekend I take on a different flower bed and destroy it kind of Pamela process.
People are saying that I am low and you are high. So let's just just keep talking. I'm sort of seeing what my
Okay.
levels are doing.
And I should do the same.
You
And
seem
I
a
probably need
little
Audacity
higher than
open to
me,
do
but
that.
not dramatically. I'll bring it down a little bit more. There.
So, oh my God, things won't stop launching.
It's been great. What a great day yesterday with friend of the show, of course, Space IL,
Yeah.
sending their lunar lander to the moon. Hold on, I'm gonna say hi to some people. Hi to
Okay.
Andy Cowley, Arnold Post, Ben Kalo, Bill K, Bort Clankard, Daniel McCool, Enoch, Giselle Sabrin, Guido Bibra, Henrik Bo Anderson, James Aberson, Janelle Duncan, John Drake, John Hamilton, John Power, John Seffield, John Victor, Johnny Zed, Kevin Ayers, Kaylee Cerna, Maeve the Brave. That's awesome. Nancy Graziano, Richard Hayes, Ronald McCoy, Tad Awesome, Tim Hayes, Umu, and Zapvan. Hey, everybody. Yeah, so we're going to do a double episode today. So we're going to get right into the show. We're going to record the first episode, and then at some point I will shut that down, and then we will start up a second episode, and we'll go right in. So I'm not going to have any time for question shows because then I've got to run kind of immediately. But
And we will be thanking our Patreon patrons
don't
at the end of
forget.
each of those episodes, as long as I don't forget.
Yep, I'll try
And
to
this is
remember
your
as well.
reminder.
Yeah. And
If you want to hear your name, people out there, if you want to hear your name, you just have to donate enough money. So go to patreon.com/astronomycast and let us pay Susie. Please. Please.
all right, tell me when you're ready to press record.
Yes. I'm pressing record. I'm looking at my levels.
I have also pressed record. My levels are also okay.
I have to turn my space heater off. I'm sad.
Yeah, it's pronounced
Okay.
Zed. Johnny Zed. I'm Canadian. That's how you pronounce the letter Z.
It actually sounds super cool when you say it that way.
I'm going to stop my recording. Tell me when you're ready to press record again.
Oh, I had just kept recording. Now I will
Oh,
stop and
okay.
kill that. Um, Gah. Stop. Why won't you stop? Okay.
Say when.
I am recording again.
I'm also recording again.
Okay.
Here we go. Astronomy Cast, episode 519, Transients, part 1. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Great. I think this is like the last time that we will be promoting this, but I want to make sure that we do this, which is to let everybody know about the All Stars Party, which is going to be happening in June this summer with me, Pamela, Paul Sutter, Skylius, John Michael Gaudier. Awesome telescopes. We're going to be hanging out in the desert near Joshua Tree, and we are just going to be your personal guides to the night sky. So if this sounds like something that you want to do, staying in a really cool hotel, eating fancy food, and working with telescopes every evening. So this is a thing that you want to do.
I will hug a tree.
I
will hug a tree.
Yeah, I can't wait to see the Joshua trees. So go to astrotours.co and search for the All Stars trip and check it out. And I think this is the last time that you will hear about this. Then we will have received all of the reservations will be cut off at the end of this month. So,
and if you can't make it in June, we fully understand. But we're taking turns doing awesome trips, and the reason we're doing a back-to-back episode today is because someone is getting ready to go to Costa Rica.
That's right. Yeah, I will be. Well, after the 3rd, Paul Sutter and I will be in Costa Rica with, again, 30 of our closest friends, going to see volcanoes and cloud forests and, of course, all of the wildlife, bugs, birds, many different kinds of monkeys. It's going to be awesome. So this is just another example of one of these Astro Tours. So if that one you can't do, if you can't do the All-Stars, go and check out Astro Tours. We've got trips going to Iceland. You're doing the American Southwest, and more all the time.
And you are all welcome to join me in August for the American Southwest.
All right, let's get into it. Astronomers have found that sometimes the universe changes. Things move, things explode, things get brighter or dimmer. In fact, knowing this has helped astronomers discover some very important aspects of the universe. Today, we begin a 2-part series on transients and their role in astronomy. All right, Pamela, transients. What's the plan here? We're going to do inside the solar system this week. And then next week, we're going to cover outside the solar system, and it will probably be 2 episodes. I don't know. Outside the solar system almost feels like a 3rd episode. So this may turn into 3. And you're like, what should I do? But I wonder if it's like solar system and then Milky Way and then extragalactic transients. But who knows?
Okay. We'll sort as we go.
Yeah. Always our multi-part series have no fixed ending. So what is a transient?
Put most simplistically, it is something in your astronomical data that is there one moment and gone the next, where one moment might be several minutes to several days, but not very long at all.
And it really feels like we are moving into this new age of astronomy. Up until this point, everything took so long. You would go out and you would take your telescope and you would set it up and you would take a picture and you would get the galaxy or the star or whatever it is that you were taking a picture of and you would study it. But the reality is that the sky is changing from night to night. Things are getting brighter. Things are getting dimmer. Things are exploding. Things are crashing into each other. Things are disappearing. And it's these moments that are time-based that are really hard to catch. And it's only with our modern technology now that we're starting to really get our handle on how much the universe is changing. So how much is the universe changing?
Well, we don't fully know the answer to that, and we won't until they finish building the Large Synoptic Survey telescope. But right now, from what we can tell from all the different surveys out there, from pan stars to the Las Campandres surveys to the Palomar and now Zwicky transient surveys, it seems like there is a whole lot of flicker, flaring, moving, and busting a move that is going on out there where we never know quite what is going to interrupt our field of view, no matter where it happens to be pointed. And we started to realize this as soon as we started doing surveys. SOHO was, I think, one of the first big moments of, oh, we can use this thing, a solar orbiter, a solar observer, rather, to find things other than its intended target. I mean, we know where the sun is. We don't need to find the sun. But the unexpected thing that came out of SOHO is it is chewing out sun grazing comet to sun plunging comet, one after another after another. And these comets that are in most cases diving towards their death, these are transient objects of the here today, never coming back tomorrow variety.
I mean, I would classify that into the things crashing into other things. But just
Yes.
this example, I mean, even this idea of having a field of view. I mean, anyone who has ever done any astrophotography at all, you set up your telescope, you do some 300-second exposure of the sky, and what do you know? There's a line moving all the way through your photograph that you weren't intending to take a picture of, but it turns out you took a picture of a satellite or you took a picture of an airplane. And when you think about those first asteroids that were ever discovered, they were discovered because a thing was moving through their field of view.
I think the earliest discoveries of transient objects can all be described as someone looking in their eyepiece or looking at the output of their camera CCD and saying, what the expletive? Because they were seeing something they absolutely did not expect. And transient phenomena can be that asteroid that you don't expect to see creeping through your field of view. It can be Uranus or Neptune passing behind Jupiter when you don't know they're there. It can be so many different kinds of things. And this is where the study of transient objects causes us to do a series. So when we go specifically looking for transient objects here in our solar system, we have three basic strategies. The first is I'm just going to take a image and see what I find. So this is where we have with observing the sun, we find comets. With doing studies of background galaxies, we may discover asteroids. So that I'm taking a picture of one thing and I discover something locally as an accident. That's one unintentional strategy. What happens more often is you have people that either purposefully survey along a specific area of the sky night after night after night, looking for things that change or move, or even better, they start tracking their telescope at a rate similar to the rate that they expect either asteroids or Kuiper Belt objects to be tracking through their field. This causes background stars to be straight lines across your image, and if you got the speed right, causes those asteroids or Kuiper Belt objects to be still points of light in your field.
Yeah, if you've ever seen, people have done that. Like if you want to take a picture of a comet, there's sort of two ways to go about it. One is to take a long exposure of a comet, and then the comet becomes this blur that moves across your field of view. The other way is you track the comet, and as you said, the stars turn into these blurs across your field of view because the comet is moving. So I think, if we were to like classify the kinds of transient things that are happening here in the solar system, we've got things that are moving. And those are, as you mentioned, the comets, the asteroids. So what is the technique that astronomers will use to find these things that are moving?
Well, it all comes down to survey images and a technique called photometry. This is where you simply measure the light across your image, looking for those places on your image that have more light or less light. In the case of, well, you have an asteroid blocking a star that was there previously. And by looking for these changes in light in registered images, images that have been lined up one with another, you can see, well, all this background stuff, it's not moving. So the registered images, you don't see a change in the non transient stuff. And those transient objects, they're the things that are either changing in brightness or changing in position. Either way, your given place on your image has a change from one image to another. And one of the easiest ways to make this visible is you register two images, you line them up on the stationary objects, you adjust them so that those stationary objects are more or less the same brightness. Subtract one image from the other so that your stationary objects get subtracted away. And where you have a black spot in the resulting image, that's where the subtraction led to a bright object getting subtracted out. And the subtracted image had the thing in it. And where you have a bright spot, that's where the object you subtracted from had something in it. And what's cool is with slow moving objects, you'll actually see a bright spot and a dark spot side by side in these registered and subtracted images.
And for a lot of astronomy, people are always like, "What's the point, right? Why will any of this matter to me?" But in this one field, for example, this technique is used to find the potentially dangerous asteroids that will crash into the Earth. So,
It's also used to find the potentially interesting objects that will be visited by the New Horizons spacecraft. And that's the cool thing about this is it's a technique that you can use with your backyard work as well as a technique that gets used by some of the most advanced spacecraft in our solar system.
now, we just recently, actually, I think about a week ago, had an interesting opportunity. I don't know if you were following this, that an asteroid was going to passed in front of the brightest star in the
Mm-hmm.
sky, and this is another kind of transient that we see here in the solar system.
Right. So this was an occultation of the star Sirius by a asteroid with a extraordinarily hard to pronounce name, and I'm not going to embarrass myself. It will be in the show notes. And there was a line across the world spanning north to south that if you were located somewhere along this line, you had a chance, depending on the unknown geometry of the asteroid, to see the brightest star in the sky wink out for a small moment. Exactly how long that moment is depends on the geometry of the asteroid. If we have a dog bone shaped asteroid flying through space, such that its long ways is the ways that goes across the star, it will blink out for a longer period of time. If instead we have that same dog bone, but it's aligned so that its long axis is perpendicular at a right angle to its motion, its skinny bit will instead pass over the star, and you'll see that blocking out of the light for a significantly shorter moment. Now, depending on exactly where you are along that line of potential occultation on the planet Earth, you'll have a slightly different lineup between you, the asteroid, and the background star Sirius. And so, by combining measurements of how long the star appeared to disappear for observers all along that line, we can actually get a really cool mapping of the shape of the asteroid, the silhouette of the asteroid against the sky at that particular moment in time.
And some of the most fascinating discoveries about asteroids and comets and Kuiper Belt objects in the solar system have come from these occultations, these changing in brightness. The dog, people can't see, but the dog is really wanting Pamela's attention right now. It's pretty hilarious. Do you need to do anything to get this dog to go and settle down? No?
No,
Is it
this is just
hopeless?
her. I am bored. Can you please pay attention to me, Susie? You're gonna have to cut this out. I'm
Yeah,
sorry.
yeah.
Stella is
Or
just
leave
being.
it in, whatever. Yeah. So, I'm going to give some examples, but I'm sure there's some others that you know of as well. Things like finding moons around asteroids, things like finding rings around asteroids, discovering moons around planets. That it's these occult, like discovering atmospheres around Pluto, things like that. It's these occultations where as you see this change in brightness, where you have this moment to make these additional discoveries. And in a future episode, we'll be able to talk a lot more about occultations and some of the really amazing discoveries out there. But just this technique gives so much.
It makes the invisible visible. It allowed us to measure new aspects of the thickness of Saturn's rings when they were edge on and occulted the star Mira. All these different ways that light can get blocked, that gives us new information. And we're so used to thinking of, well, how do we study things by measuring the light coming from them? This is a case of how do we measure things by how they prevent light from getting to us. And variations in light also can be an extremely powerful tool for doing science. One of the other things that we do with asteroids is we don't just measure where they are in an image, we measure how bright they appear in an image. And variations in the brightness of these bodies actually allow us to get at how are they rotating, how are they tumbling, how are they shaped, and it puts limits on our understanding. We can't get a complete understanding of an asteroid's shape by how it reflects light. But if we see one moment it's significantly brighter and the next it's significantly fainter, that gives us a sense of either we're seeing it on the big flat side, or now we're seeing it on the small tiny side, or maybe one side is significantly more reflective than the other. That's not generally the case. So probabilities tell us that we're seeing an asymmetric object tumbling through the sky.
So one interesting mystery that has transient baked right into the name, transient lunar phenomena, was was considered like a legend for a while
Yeah.
there. Astronomers were seeing bright flashes that were coming off of the moon, and for a while, like amateur astronomers were seeing them, and other astronomers weren't believing it. But now we know
Right.
this is a very real thing.
And I first learned about this when I was a graduate student working out at McDonald Observatory. A astronomer from another university, Arlen Kratz from Columbia, he would come out and use McDonald Observatory for his research. And one of the projects that he was doing was looking for bright flashes on the dark part of the moon. So you look at a crescent moon, you point your telescope at the part not being illuminated by sunlight, and you look for flashes in that shadowed region. And I remember talking to him about a paper he had up at the Lunar and Planetary Sciences Conference one year. And at the time, it was unclear, are these outgassing events that are somehow giving off light? Are these collisions? Are these just flukes in the data? And he was certain they were real, but wasn't certain what they were. Well, now we know that rocks are still falling out of the sky and hitting things scattered throughout our solar system. We have seen new craters arise on Mars. And recently we saw what we expect created a new crater hit the moon during the last lunar eclipse just a few weeks ago. There was a global phenomena where half the world had the opportunity to look up during that eclipse and see a bright flash occur along the edge of the moon. And that bright flash is thought to be a impact that was imaged by multiple telescopes, seen by multiple eyeballs. And this is the first time this is known to have happened since a whole group of monks couple hundred years ago were all looking at the moon together and saw something like this. So to go from an experience shared by a group of theologians living together in Europe to something shared by half a planet is pretty extraordinary.
Yeah, I was live streaming the entire lunar eclipse. So in theory, I've got a picture of that. I haven't gone back through my data yet, but it's in there somewhere, I would assume.
And this was definitely one of those moments where you find out just how careful an observer you are, because the fact that there are some people who were able to just be standing there watching
Yeah,
through
and
their
see it.
telescope, yeah, um, that's amazing acuity. I am much more of a let's digitally compare things and figure out what moved. And one way to think about this is Pluto, when it was discovered by Clyde Tombaugh, was actually just a transient object moving through the background stars. And that blink comparison method that Clyde Tombaugh used to find that thing that didn't stay put across multiple images, he was looking for a transient object and he found it. And throughout his life, it managed to stay a planet.
Right, for his life anyway, but not after that.
Yeah.
So what are some other examples, some other transient phenomena that astronomers are looking for here in the solar system?
Well, we don't often think of it this way, but coronal mass ejections and other solar flares are transient phenomena. We usually think of solar flares, stellar flares, as being transients for astronomers to observe. But it turns out there are solar observers interested in these things as well. And if they're a transient to the astronomer looking at a far off star, they're a transient phenomena for people looking at our nearby star. So we have sun grazing comets, we have regular comets, observed different ways. Sun grazers, we're using things like SOHO, SDO, looking to see them plunge in through these dedicated observers looking at the sun. We have the sun's transient phenomena itself moving outwards. We have asteroids in all their different orbits. We have Kuiper belts objects, the icy objects in the outer solar system. We have all the random, we're not sure if they're asteroids, comets, or something in between. And then we have the really weird stuff like Oumuamua. It's not aliens. It's never aliens until it's aliens. But Oumuamua was a transient phenomena that, like a sun grazer, is never coming back, but it didn't commit death into the sun. It just left our solar system altogether. It noped us and said goodbye and flew away. So that is yet another transient phenomena. So basically, at the end of the day, transients are all of the rocks, ice, debris moving around. And it's also the things they create. It's the stars they block out. And, the one thing we haven't talked about is another form of transient phenomena is those dark spots we sometimes see on Jupiter, those bright flashes of light we sometimes see on Jupiter when it gets
Yeah.
hit. Now, do you remember where you were back the summer of 1994 with Shoemaker Levy 9?
I was I was in Vancouver working at a software company. So I do remember sort of watching that as it all came. Or was it 94? Was it 97?
It was 94.
It was
It
94.
was the
Okay.
summer
Yeah.
between my sophomore and junior
Yeah.
year of college.
Yeah, and I do remember sort of everything leading up to that, and I was interested in astronomy. I wasn't doing it as a career yet for another couple of years. But
And
yeah, no,
and this
absolutely.
was this was an event that you could see through a backyard telescope, those dark spots arising on Jupiter. And at the time, we thought this was a once every 500 years kind of event. And what's been amazing is to watch in recent years as the price of digital cameras has come down, as more and more people have bought CCDs, have set up robotic telescopes. It seems like almost yearly
Yeah.
now, someone catches something hitting Jupiter and giving it a
Yeah.
big black spot.
I mean, we did an article probably about 6 months ago about how people are still discovering objects smashing into Jupiter and releasing a flash. In our remaining time, I just wanted to, like, I think what's great about transients, like almost like whenever there is a new field of astronomy that really opens up, there's this space for amateurs who are dedicated to be able to really make some serious contributions into this science. So if people are wanting to be a part of this, what's a kind of setup, and where could they maybe get involved in some of the projects for helping out here in the solar system?
So for the solar system, the best thing you can do is find out about how to join the Minor Planet Center. It's an organization that is run by the International Astronomical Union and based out of the Harvard Smithsonian Center for Astrophysics. And the Minor Planet Center will start out by saying, okay, go out, observe these known objects, and report back what you see. Give us your brightness measurements, your position measurements, and build up trust. And once you've built up that trust, they'll give you an observer code and set you free to go out and begin discovering asteroids. And what gets me is there are so many unmeasured rocks out there
Yeah.
that amateur astronomers are continuing to find new asteroids on a regular basis. It's getting harder because there are so many automated large surveys out there, but there's still space for everyone to make their own discovery. So start with the Minor Planet Center and then stake out your own corner of, well, right ascension and declination and make it your own.
Yeah.
Get to know what's supposed to be there and find all those interlopers sneaking into your field.
And you don't need that powerful or expensive a telescope. It's there, you probably want a photometer. You probably want like a nice CCD to be able to do some photometry. But even a 6-inch and 8-inch telescope, what it is it's about practice, and it is the unthrilling work of night after night observing a chunk of sky at the greatest detail that you can, and comparing that with what's supposed to be there and finding out if there's anything new. So this is, I mean, we're really serious. Like if this interests you, and even if you're an amateur and you've always wanted to be an astronomer, for $1,000, you can do real science and provide a real benefit to the astronomical community. You can discover asteroids. One of the great things about asteroids is that you can, if you discover them, you get to name them. I have an asteroid named after me. Yeah.
I do not.
Yeah, I know. So somebody discover an asteroid and name it after Pamela. That's only fair. All right. Well, Pamela, this was great. Next episode, we'll be talking about what is outside the solar system as the universe changes. Thanks a lot.
Thank you. Bye-bye, everyone. Wait, stop.
Oh.
We have to read names. We have
Do
to
it.
read names. All of you on Patreon, I love you. I don't mean to keep almost forgetting you. And I'm now going to thank a group of you. So our special thanks go out to Brian Cagle, Helga Bjorkhag, Bill Hamilton, Greg Thorwald, Richard Riviera, Josh Cunningham, Silva Westby, Jeff Collins, Merrick Verdarni, and John Drake. And I will be reading more names at the end of the next episode. And if you want to hear your name said with joy and emphasis on happiness and thanks by me, check out patreon.com/astronomycast. And thank you, all of you who make our show possible.
Thanks, everybody.
Bye.
That was close. I almost clicked save.
Yeah. Okay. This is 518?
This is 518. No, 519.
Okay.
And then we'll just start up 520.
Mm-hmm.
I'm ready when you are. And
Okay.
so, do you want me to try and mentally keep this to just the Milky Way, or should we just go to everything? How are you feeling? I mean, we've got mirror variables.
I
We've
I'm happy
got
to do, because the
flare
only
stars,
extragalactic to
novas.
bring up is BLAC objects, basically. So we only really have one extragalactic, unless you want to leave visual and start picking up gravity waves and stuff.
Yeah, I mean, supernova is the only extragalactic transient.
Well, no, you also have variable, you have active galaxies that vary and
Right.
go into outbursts periodically.
Yeah. So okay, well let's just do it as one then. We'll just merge it
Okay.
all into one thing. Okay. So this will be the end of the series. All right, no problem.
Okay.
Let me know when you're ready to press record.
Okay. I have pressed record. I am recording.
I am also recording. Ready? Here we go.
I hope so.
Astronomy Cast, episode 520, Transients, part 2. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Great. For the people who are listening to this show, it's been a week. For us, it's been about 5 minutes. That's because
Not even that
not
long.
even since we wrapped up recording our last show to when we're doing this show, because I'm going to be gone next week, and so in fact probably when you're listening to this, I will be in Costa Rica with Dr. Paul Sutter. Will be as part of our Astro Tour as we explore the jungles and beaches and mountains and volcanoes and the dark skies of Costa Rica. And if you want to be a part of any of these kinds of trips, go to astrotours.co. Pamela's going to be taking you to the American Southwest. It's possible that I'm going to be going back to Iceland at some point. So there's a lot of really interesting trips coming up. So check it out.
And I hope to see you in Tucson and Vegas.
Excellent. All right, this is our second episode in a two-part series where we look at transients in astronomy. Last week's episode, we talked about the things that change here in our own solar system. Now, we'll talk about everything else in the Milky Way and beyond. All right, Pamela, when last we saw our heroes, we were talking about asteroids and comets and things crashing into the moon and things crashing into Jupiter and potential extrasolar comets blasting through the solar system. But this idea of transients, the fact that the universe changes, extends out way beyond the solar system, all the way out.
It is true. It is true. And the techniques that we use to observe transient phenomena don't really change, but how they move through our images, how they vary in our images, does change from inside our solar system to outside our solar system. Let's face it, things inside our solar system, it's a lot easier to see them moving. And so the fact that an asteroid is flying by the Earth, that makes it a transient phenomena. Now, as we look out at the sky, the fact that Bernard's star is creeping across the sky at a measurable rate does not make it a transient
Right.
object.
Right.
That just makes it an object that has a large motion.
Well,
Now,
that's astrometry. I mean, that's a whole other super
yeah,
fascinating science. And thanks to Gaia, we now know where 1 billion of these stars are moving. But yeah, it's things that move or flash or change more rapidly than that ponderous movement of Bernard's star.
and it's the kind of thing that a lot of people don't realize is going on. One of my favorite moments of oh dear, that doesn't work the way you think it does, was reading Keats' poem where he referenced wanting a love as constant as the stars. And stars are anything but constant, and they
Oh,
sometimes
Keats.
explode. And I don't want that kind of love. Thank you very much. Please keep mine as constant as a rock.
Sometimes they
Uh,
change in brightness and sometimes they explode, just like real relationships.
yeah,
And they're
yeah. It
all
doesn't mean
moving,
you want
and eventually they end up in a black hole.
that. So Keats was so wrong in what he thought he was going to get. And in considering that, let's consider all the things that go flash, flare, and flicker in the night. And one of the things that came up in our last episode was how our own sun likes to do things like fling coronal mass ejections out at us. And it turns out that while our sun, from our perspective, does throw some pretty amazing temper tantrums that lead to some pretty spectacular aurora borealis, it turns out that it has nothing on some of the other stars scattered out among our galaxy. There are young protostars that put out flare events that are 10,000 times more energetic.
100,000 times. Some of the flare stars can go 100,000 times brighter than the most powerful flares that our sun throws out. Tiny little
And
red dwarf stars. It's
and
crazy.
there are some stars that are known to do this more often than others that get classified as flare stars, but this is definitely one of those cases of having to get lucky when doing your research, because there is a chance, a non-zero chance, that every single time you go to the telescope and look at a star, it's just going to be going, "Hi, I'm a star." And what you really are interested in is that moment it goes, "Hi, I'm going to destroy my entire solar system with a flare
Yeah.
right now."
Again.
And those are the scientifically interesting moments. And so the trick is, how do you catch all those moments?
How, well, you just asked yourself my next question. How do you catch all of those moments?
Well, in the future, it's going to be with the Large Synoptic Survey Telescope, at least for the part of the sky that it can see. For now, we have a variety of different surveys scattered all over the world looking at different parts of the sky that are night after night working to observe as much of the visible sky as they can and comparing the measurements of brightness from one night to the next to identify those things that have outbursted in their own unique way. So we have flare stars. That's one way. Those are often young stars, hot stars, energetic stars. B-type stars like to flare in some cases. And all of these hyper energetic young stars, angry stars, they aren't at least blowing themselves apart. We
Right.
also have cases where we don't know which star it's going to be. We don't know when it's going to be, but let's face it, supernovae are another kind of transient event. They are that star that explodes once rather than flaring over and over and over.
Right. Well, one of the things I did an episode on habitability around red dwarf stars, and we looked into these flares that happen, and yeah, the 100,000 times the amount of radiation, like, you would cook any life, and these planets are much closer to their star than we have here at the sun. Like, you can't comprehend the amount of energy that is being dished out to one of these planets, and that some of these stars flare every day. Like, it's crazy how different these places are than the sun. But as you said, there are other ones that will flare. Now, you went straight to things exploding, but there's an in-between stage.
Oh, yeah.
So
Well, there's lots of in-between
lots of
stages.
in-between stages. So, why don't we talk about novae first, and then we'll go full supernovae next.
Okay. We have basically the life and death of stars is one of change. Baby stars like to go flare a lot. Middle-aged stars pulsate. That's not so much as a transient event. It
I
is a
guess we should talk
change in
about like
brightness.
mirror variables. Yeah.
Yeah. So we have all the pulsating variables, the Cepheids, the RR-Lares, the Myra variables. We have the
Actually, you know what? I'm
random.
going to stop you, because what's actually happening with some of those different kinds of variable stars is mind blowing. Like, if you could actually see them up close, what's actually happening to these stars is just tremendous. So instead of just like naming them like it's some kind of library catalog, can you just take a second and talk about? I mean, we did a whole episode on those variable stars, but just to give people the sense of some of the most dramatic versions of this.
So stars are very carefully balanced between gravity trying to collapse them in and light trying to push out and expand them. And a star like our own sun is, for the most part, nice and completely stable in radius. It has various harmonics built up on its surface, various sound waves are moving through its outer atmosphere. And so it has these little small scale pulsations from place to place. No big deal. It's a star. It's doing a star like thing. Well, at certain points in stars' evolution, as they very gradually change in density, temperature, and radius, they can hit a point where, as the light goes out, the temperature is such that instead of pushing outwards on the star, that light starts getting absorbed into the gas in the outer layers of the star. And so the star's like, ooh, not getting supported as much as I'd like, gonna collapse now. And as it collapses, it gives off, it gets brighter, it gets brighter, it gets brighter. And that energy that is stored in the atmosphere also gets given off, and all of this gives the star an extra push, expanding it outward. And so a star will hit a resonance point where it is collapsing down and pulsating out, driven by energy getting stored in the gas in its outer atmosphere. This sets up long-term pulsations that can last millions of years in elder stars. The RLRs I mentioned are small ones that pulsate over a period of hours. Cepheids are larger ones that pulsate over periods of days or tens of days. And when I say pulsate, I mean they're actually changing radically in radius, in color, in brightness, such that we can see stars in other galaxies undergoing these kinds of pulsations.
Yeah, just amazing. Like, can you imagine what it would be like to be on a planet around one of these stars and seeing the outer envelope of this star expand over the course of hours to a dramatically larger size, and then again over the course of hours shrinking back down into a much smaller size and changing in brightness. It would just it's one of those things. People always ask me, like, what's a thing that you wish you could see up close? And I wouldn't want to be too close, but I would love to see one of these variable stars doing its thing from a
I
safe
now
distance.
I haven't done it before, and I should have. I now really want to work out the change in energy received by a planet that is on average at the center of a habitable zone for one of these stars, and see, does it go in and out of the habitable zone at the extremes?
Yeah.
This is math I can do and I now want to do. Oh
Okay,
man,
great.
you're giving me ideas.
Nice. There you go. And then it'll turn into a science fiction story. So, all right. So we talked. Now I was about to get you talking about novae, and then I turned into variable stars. But let's go back to novae now, which are like the
Okay.
next level of flashes of brightness.
Right. So there are a whole variety of different nova that recur at varying levels. There are some nova that we see that repeat like clockwork. These are ones where you have a situation with a white dwarf star, a star roughly the mass of the sun that is compressed down to roughly the size of the moon and is no longer generating its own light through nuclear processes. It's just radiating away the heat that it has stored from when it was a star. And if one of these is in a binary system and it decays to get close enough to its neighbor, it can become a cannibal and begin stripping material off of that neighbor. And as that material spirals in towards the white dwarf, forming an accretion disk, that disk of material can periodically get large enough in mass that it just blows itself apart. So in this case, you have recurrent nova that are driven by, well, cannibalism of one star off of another. We also have cases where it's unclear, do these things recur consistently or not, and various levels of do they recur consistently or not, where you have, again, a white dwarf cannibalizing its neighbor, where it pulls down the material and the material on its surface goes kaboom, clearing off the surface, clearing out the accretion disk. It's a little bit more violent. And each of these kinds of situations has distinct spectra, has distinct patterns. You can actually look at some of these stars from night to night and see the variations in brightness as that hot disk of material moves around and is viewed at different viewing angles. These are fascinating systems that change in brightness because they are binary stars, because there is this hot disk giving off its own light, because this disk may explode occasionally, and because stuff that lands on the surface of the star may explode occasionally. There is a lot of explodiness going on in this system that finds all sorts of different ways to have transient light in the sky.
And actually, we just did an article on Universe Today again about a nova that's been going off every year like clockwork for millions of years. So it's this process where it's pulling this material off of a companion star, accreting it onto the surface. It builds up to a certain size. It detonates like a bomb off the surface of the white dwarf, and then the whole process starts again. It clears out the material, and then it starts again. And it's been building this gigantic gas, this sort of shell of dust and gas around the star from millions of these nova explosions. But for each one of these white dwarfs, there will be the final explosion.
So that material funneling down onto the surface of the star doesn't always get politely cleared off through explosions. Sometimes it just gradually builds up and builds up and builds up until the total mass of the white dwarf exceeds essentially the supporting power of the electron degenerate pressure that is holding the star together. So in these systems, it's not light pushing out and gravity pushing in that is supporting the star so that it doesn't collapse down into a black hole. Instead, it's all of the electrons in the atoms of the white dwarf that are going, don't come near me. And
this is my space.
It's the electron degeneracy pressure of all of these electrons trying to abide by the Pauli exclusion principle and all maintaining their own energy levels, spin up, spin down, not going to break any rules. Well, at a certain point, they just don't have the capacity to push one another apart and through this electron degeneracy pressure support the star any longer. And when that electron degeneracy pressure gets overwhelmed, everything goes kaboom. And this is when you get a type 1a supernova.
And this is just one example of a supernova. There's the ones where you have a big, young, hot star. And of course, we've done whole episodes of this, and they detonate, or they are left with a black hole, or they're left with a neutron star. And each one tells a story that astronomers can use to understand what came before. And as we mentioned as well, they are used as standard candles to help understand the distance of things in the universe.
And these two different objects, supernova and asteroids discussed in the last episode, are really the two main justifications for all these global surveys that are going on of the sky, where we're trying really hard to understand what is the future of our universe. Will we die by fire or ice or great rip? And I don't even know how to consider that. And that future evolution of space-time is going to be defined by understanding the rate at which our universe has been expanding since the earliest days, which we see through supernovae. Now, the other thing is, how is the Earth going to live and die? And hopefully death by rock is not our definitive future. And the way we prevent ourselves by going the way of the dinosaurs is by finding any rock that is potentially going to hit us. So when we go surveying for transient objects, when we build all of these different telescopes designed to find transient after transient after transient, our justifications are measuring the future of the universe and preventing death of the planet Earth. But all this other science is like free extras. So I have science for you, I have science for you, I have
Right,
science for
right.
me in the form of all of these Cepheid variables. And fundamentally, even the Kepler telescope with its planet hunting capacity was a transient searching telescope where it was looking for the changes in brightness due to planets passing in front of the stars.
And that's where I was going to go next, right? We talked about in the previous episode, we talked about this idea that we can observe stars and watch occultations as an asteroid passes in front. The universe is a really big place, and things pass in front of other things all the time in ways that are really amazing and teach us a bunch of really interesting stuff about the universe. So can you talk just a bit about the transit method of transients?
So in this case, we have a distant system that has its own planets, its own asteroid belt, its own disk of material. We've seen examples of all of these kinds of phenomena. And that distant solar system stuff passes in front of the star that it calls its home star and blocks out some of that star's light. And we can learn about what is doing the blocking by how that transit occurs. And we can, by measuring the star's motion in and out of the plane of the galaxy, by measuring how it gets Doppler shifted, is the scientific way of saying it, we can measure how much mass is in that material. And we can start to get really cool and detailed measurements of distant solar systems that start to give us more detailed pictures of how normal or abnormal is our own solar system. And it's looking like we're pretty weird.
Right.
And
We thought we were
that's
normal. We're
kind
not
of
normal.
no.
But you mentioned like when we were talking about, for example, when you watch an asteroid pass in front of a star and dim the star, depending on where you are on Earth, you can learn different characteristics about the asteroid. You can learn whether it has a moon, whether it has a ring, whether it has an atmosphere. There are all these really interesting things. So what can you learn about the object that is passing in front of the star, and what happens when a star, actually we'll get to that in a second, but like when stars pass in front of other stars?
So with planets, disks passing in front of their home stars, the two basic pieces of information that you can get at if you have like a nice discrete planet is what is the planet's radius, what is its distance from its home star, and what is its mass. Now, for these three things to all happen, you need to have a planet that eclipses its star, passes right in front of it, allowing us to measure how long it takes to get in front of the star, how long it takes to get out from in front of the star. That gets us its radius. We need to be able to see this multiple times. That gets us its period of motion. And if we can measure the Doppler shifting that's going on, how that planet is in turn using its gravity to move the star that it's going around, that will give us its mass. So we can get pretty detailed understandings. Now, one of the other weird things that happens is there are examples out there of disks of material going around stars that get involved in this whole eclipsing act, leading to some really weird long-term eclipses. Now, these kinds of events don't allow us to measure the mass in that disk, but they do allow us to say, yeah, other stars have dust disks. And even that is pretty cool science.
Yeah. Um, the and then sort of take that to the next level, right? You can have this situation where the two stars are perfectly lined up so that one acts like a lens to the star that's behind it. And that star that is lensing, you can then learn a tremendous amount about that star or the one that's behind
And
it.
this is gravitational microlensing. And so what we're looking at And this was done a lot by the survey projects Macho and Ogle that looked at the large and small Magellanic Clouds and towards the inner spheroid of our own galaxy, and looked to see, do any of those background stars suddenly appear to get brighter because a foreground object has passed in front of it, and that foreground object's gravity bends light that would otherwise never get to our telescope into our telescope, well, into the telescope of everyone in our general direction. So that gravitational bending that gets extra light to us, the observer, that's the gravitational lens part of it. And it tells us where that otherwise hidden material is, and has actually allowed us to see stars that have planets that potentially have moons in places that we don't otherwise have the capacity to be looking for planets. It allows us to go looking for, well, are there rogue Jupiters wandering our solar, not our solar system, wandering our galaxy? Answer appears to be no. What is the number of rogue black holes out there? Can you use black holes to explain dark matter? The answer appears to be no. So these searches for gravitationally lensed nearby stars getting that are lensing background things in either the galactic spheroid in the center, or in the Magellanic Clouds, these events help us find the invisible material that is in our galaxy, and help us realize just what is the diversity of stuff that we don't otherwise get to see. It's gravity making the invisible visible.
And the one thing as we start to wind down this episode is we're very familiar with the sorts of things that we can see, and all the things that we've talked about today are all about using phenomena that essentially visible light, the kinds of things that you would see in your normal telescope. But there's a whole bunch of other transient phenomena that exist in other wavelengths, things in the radio waves, things in the X-rays. So can we just talk briefly about that? That once you expand what you're looking at, another whole level of interesting changing objects show up.
So this is where you start to get magnetars, neutron stars with extremely strong magnetic fields that periodically rearrange their magnetic fields and give off massive amounts of gamma ray radiation. This is where you start to be able to look at distant, actively feeding galaxies like the BL-LAC object and see flickering and flaring in the core of a distant galaxy. This is where you start to get, well, gravitational waves are a transient event, just not one you're going to see using the photometry technique that we've largely talked about today. Gamma ray bursts in all their forms are a transient phenomena, in some cases linked to massive supernova that have magnetic fields called hypernova, in some cases linked to the crashing together of a pair of neutron stars where we also get gravitational waves. All of these different things are showing that our universe is not a constant place. It is not that unchanging place that it was thought of to be by the ancients. And unless you're a crazy person, you certainly don't want a love as constant as the stars.
Right. I love this idea that for the longest time, astronomers would pick a thing and they would look at it, and then they would study it, and then they would do some research. And then we moved to this idea of surveys, things like the Sloan Digital Sky Survey, where you would try to just take a picture of everything so that everybody could have a picture of everything that had, that was in the entire sky. But that's not enough. We are now moving to this time where we have to be able to see everything that's in the sky all the time. So it's the difference between a photograph and a video, that we are now moving to an age of astronomy that is the video version of where old astronomy was the photograph. But it's even weirder than that. This is
what we always wanted.
I know it's what we always wanted. Now we're finally getting it, right? And
right,
the final
we have the technology.
step is to, in addition, look across all of the spectra at the same time. So you're not just recording a video of the entire universe in purely visible, but you're going to want to do that in gamma rays and in X-rays and in radio waves across all the different spectrums to see every single thing that the universe was doing when we weren't looking.
And one of the biggest frustrations is while we have uh, the capability with optical telescopes to take images of a large chunk of the sky at once, while we have that capacity with infrared telescopes and some ultraviolet, we do not have the capacity to take wide angle, high resolution images in all these other colors of the rainbow. And the electromagnetic spectrum makes it hard for us to do large scale detailed surveys of a lot of the sky. But we're going to get there. We're going to get there.
Well, that's it. And so
Maybe.
we are entering the golden age of transient astronomy. And as you can see, there's a lot left for us to be able to do. So lots of work to be done into the future. Well, that was great. Thank you so much, Pamela. Oh, wait.
Thank you.
You should say some
Wait.
names.
Oh, we have to read names. Yes. Thank you. We're going to remember.
I remembered.
So we love our Patreons dearly. And we're just learning a new way to end this episode. And I'd like to end this episode by thanking a few more of our fabulous Patreon donations. This week, I would like to thank Nate Detweiler, Joe Wilkinson, Raymond Buzinski, James Platt, Jonathan Tronson, Philip Walker, Elad Avron, Paul D. Disney, anti-user, and Scott Bieber. If you too would like to hear your name read by me in an overly enthusiastic and grateful tone of voice, just support us on Patreon. Thank you so much for making this show possible. We wouldn't be here without you.
Thank you, everyone. We'll see you next week.
Bye-bye.
Okay. Well, unfortunately, we can't stick around. I've got to go run. Take a kid to a thing. So thanks, everyone. Sorry we don't have question show time this time round. But and I'll see you all in like 3 weeks when I get back from Costa Rica.
Sounds great. I'll see you later, Fraser.
Okay. Actually, no, I'll be here next Friday.
Yeah, it's 2 Fridays after
two
that.
Fridays
I wasn't
after
going to
that,
bring that up, but
Yeah. All right. See you later, everybody.
Bye-bye.
Bye.